So how do we tell the difference in the lab, in the physical world, between two enantiomers? Enantiomers are similar in a lot of ways. So here are two enantiomers, R2-pentanol and S2-pentanol. So are they the same molecular weight? Obviously. Are they the same melting point? Yeah, they're just mirror image, so they have the same intermolecular forces. So same melting point, same frequencies, no matter what kind of spectroscopy you want to look at it, right? The only way we can tell this apart is if it's in a chiral environment, like our body, right? So we talked before about how these things we can think of them as like left and right mittens or gloves, and one of these things will interact with the body differently than the other. The other way we can tell is that it turns out that chiral compounds rotate polarized light. We call that optical rotation. So it's kind of a cool thing. We're going to learn it or experience it for ourselves in our lab this week. So that's the one that I'm going to take half the class. We're going to do kind of a at-home thing. But the idea is this. Light around us goes through a polarizer. So that is this little piece of plastic that you just got in the mail from us. So if you've ever had polarized sunglasses, you're familiar with this. So a polarizer only lets certain sort of plane polarized light through, right? And so light coming through that polarizer is now plane polarized. That can go through a sample. Typically it goes through a 10 centimeter long tube full of some solution or full of some neat sample. Coming out of that, that plane will now be tilted one way or the other by some amount. And then that we go to some detector to see that. I should have another polarizer up there because we need two polarizers to do this. So in your packet, you've got this one polarizer, and then you've got another piece of plastic. Yours is going to be round. This one I've got is a quarter circle. But check it out. When they are lined up, light can get through very well. So here the planes of the polarizers are parallel. But when I rotate this 90 degrees, put this back, now they are, the little crisscrossies are 90 degrees to each other, and so no light gets through the polarized film. So A, this is why polarized sunglasses are cool, and B, if we put something between these two polarizers, it will shift the light, so it's not just simply 0 degrees and 90 degrees, right? We'll be able to see that shift in the polarization. How many degrees the light is rotated depends on a lot of things, most of which we usually kind of ignore. So it's going to depend on the wavelength of light and the temperature involved. And usually when we do this, or when you look it up in a book, they're using the same wavelength and the same temperature. The wavelength that they're using is just denoted the D line. So what that is old-fashioned sodium lamps burn a very bright yellow. If you've ever melted glass, you know that glows yellow. That line is the sodium D wavelength. It's in the 500 nanometers range. And usually these things are measured at 20 degrees Celsius. So they're not strongly linked to temperature, but technically it is temperature dependent. It's also dependent on the solvent. So when you look it up, they'll usually verify or specify what solvent it's taken in. The numbers we look up for these things are called specific rotation. So I mentioned that they depend on the temperature. So usually you'll see this alpha with this 20 for temperature and this D for the sodium D line. That denotes, again, temperature and the wavelength. And then we're going to basically compare our data, the observed data, to some textbook by taking our observed data and dividing by the concentration of the sample and the path length in decimeters. So these are real weird units, and they're only there because of history. That's how people have historically put this together. So your lab exercise this week will be to essentially prove to yourself that the observed rotation is proportional to concentration and path length. Right? So if you rearrange this equation, your observed rotation should equal some constant times concentration and the path length. So the path length is, again, what the light is going through, how far the light is going through it. And you'll be proving both of those in the lab this week. So this is great. This gives us a way to reference what we see to other labs, right? And this is a good purity check. If your sample is pure, it should have all of the rotation that it has in some other lab. And if it has less than that rotation, then you might have some S in your R, or you might have some R in your S, and so forth. Enantiomers have equal and opposite rotations. Menthol, which I drew before, rotates light -50. If I ask how much does its enantiomer rotate light, it'd be +50. Right? So enantiomers have equal and opposite rotations. Again, we can bring language into it and say, like, okay, never mind the structure, just tell me if it rotates light clockwise or counterclockwise. If it rotates light clockwise, if the rotation is positive, we say it's plus. So we'd say plus menthol, or minus menthol if the light is rotated counterclockwise. Okay. In the old-fashioned literature, you see D and L for these things. D is dextro-rotatory, L is levo-rotatory. Those are used for sometimes sugars and amino acids. So it turns out that almost all of your naturally occurring amino acids are L, not D, and almost all of your sugars and carbohydrates are D and not L. That's still kind of a mystery that we're working through why that is. But this is another kind of way to communicate about enantiomers. It's just which one rotates light this way and which one rotates light the other way. It's worth drawing some distinctions between R and S and plus and minus. So R and S, we just went through. We have to assign it for each chiral center in a molecule, and we can assign it from the structure. So just if you show me a drawing of a molecule, I can tell you R versus S. Plus and minus does not work like that. Plus and minus, first of all, is for the whole molecule, because I'm just looking to see if the whole thing rotates light one way or the other way. But also, plus and minus must be experimentally determined. I cannot look at a structure and just say, oh, that's definitely going to rotate light plus or to the right or to the left. That doesn't really work. Even computationally, I think it's very difficult. And so these are very different. Don't get them crossed up, and they're not really always linked. R is not always plus, S is not always minus. Sometimes R is plus, sometimes R is minus. The only thing that we can know is that if we're talking about one thing versus its enantiomer, enantiomers will have opposite R and S's, opposite configurations, and will have opposite rotations. Let's do a little bit more nomenclature. So let's say I've got maybe a mixture of R and S 2-pentanol. So I know that those two pentanols are enantiomers of each other. And so if I compare 100% with 100%, they'll be equal and opposite. One will be positive, one will be negative. If I mix those two enantiomers together in a 1-to-1 ratio, it crosses 0 here, and that rotation would be 0. It stands to reason that a 50% mixture of both, a 1-to-1 mixture, would have no optical rotation. For every molecule rotating light to the right, you have a molecule rotating light to the left, so everything evens out. We have a special name for that. That's a racemic mixture. It's a 1-to-1 mixture of enantiomers, or a racemate. It comes from winemaking, actually, which is how Pasteur actually found chirality in the first place. So again, nomenclature, a 1-to-1 mixture of enantiomers is a racemic mixture or racemate, and it has no optical rotation. As we get into synthesis, when we try to make something in a lab, when I try to make something chiral, most of the time, if I just take the simplest route to make it, I'm going to end up with a 1-to-1, a racemic mixture. And if I'm trying to make a drug, that's not great. That's not really where I want to be, because as we said, enantiomers have different effect on the body. If this is a good drug, then that is probably not as good a drug, or might even be harmful. And so a lot of effort is into trying to do syntheses that do not give us a racemic mixture, that give us only one enantiomer.